Hello, everyone. My name is Min Mong. I'm a technical marketing engineer for the HyperLynx tool suite here at Mentor. I'll be the presenter for this webinar, and the topic is about ensuring DDR4 electrical performance at intended data rate. The goal here is that you want to know how much design margins you have with the data rate you plan to run the memory interface at, while considering all of the electrical factors before fab out. First, I'll provide some insight into why just following the routing rules provided by either the controller or memory vendor is not good enough in DDR4 designs nowadays running at high data rates. Secondly, I will list some of the electrical considerations you need to make during the post-layout verification process. I will also explain in more details of some of these device-related electrical factors, such as why we need to consider derating and VRF training in DDR4 designs. Finally, I'll demonstrate in HyperLynx how to optimize your design margins by performing trade-offs in both memory down and multi-board with DIMM designs in the post-layout stage of your design process just before prototype. Comparing DDR5 maximum data rate to DDR2, it is 8 times faster, which means the bit periods are shrinking, translating to less timing window to work with. The I/O voltage for DDR5 is also 40% less than DDR2, which means you will have less noise margin to work with. You can see the shrinking of the I size from DDR2 to DDR5 visually here in comparison. Usually, the designers are familiar with the routing rules provided by memory controller vendors, as shown here, provided by Xilinx as an example. It provides all of the detailed routing rules such as trace width, separation, skew tolerance, clearances, stitching via placements, not to cross gaps, and so on. But let's say if you follow all of these routing rules precisely, will your DDR4 design work with maximum margins? Most of the time, just following the routing rules is not enough. You must consider all of the electrical effects and parasitics of the layout and devices, but at the same time, you must have plenty of margins for the design to be robust. Usually, if you over-design, then you might be wasting your resources, but if you under-design, then you might run into consistent or sometimes intermittent issues in the lab, or even worse, you might only find the problems during the production. In any DDR4 design, there are many electrical considerations you need to make as outlined in this table. There are 3 groups of nets which you must verify that the design meets all the timing and SI requirements specified by the JEDEC specification during the write cycle. During the read cycle, you must meet all of the electrical requirements specified by the controller vendor. You must also include the effects of the items listed in the second column here during your post-layout design investigations. For example, trace-to-trace and package coupling effects could either affect your margins significantly or not, depending on the drive strength and termination values you use. Another example is that you must account for the worst corner cases of the devices to ensure that your design still have expected margins. I'll show in the demo on how these effects can be simulated in HyperLynx on both memory down and multi-board DIMM cases in this webinar. Non-ideal PDN effects need to be investigated as well on how they affect the margins, but we'll cover these effects and simulations in a future webinar. In this webinar, we'll assume ideal PDN. You will also need to consider these device-related factors as shown in the third column in your post-layout analysis to maximize SI and timing margins. I'll cover some background info on some of these items next in case if you're not familiar with them. For example, I'll cover why do the controller need to perform VRF training and DBI and how they can affect your design margins. I'll also show in the demo how these factors can be varied or included in the post-layout verification process using HyperLynx. As previously mentioned, 3 groups of nets need to be verified. The data bus is bidirectional, so we will need to verify both read and write cycles with iMask. The address command control or ACC bus needs to be verified during the write cycle at the DRAM with setup and hold and some SI requirements. There are skew requirements which need to be met as well between DQS and clock during the write cycle. Next, I would like to cover some background info on I/O technology for data bus. One of the major market forces acting on the DRAM industry is the demand for lower power consumption of the memory devices. To this end, DDR4 uses the new drive standard known as pseudo-open drain or POD. In POD, the receiver terminates the signal to a high level or VDD rather than to half the rail voltage or VDT. When driving to low state, there is a current drop. However, when a high is driven, it draws no current as shown here. DDR4, however, requires that the VREF be generated within the DRAM and be adjustable. Note that in this situation, the center voltage value is dependent on not only the supply voltage, but also on the characteristics of the transmitter and receiver. In this example, as you change the ODT settings, center of the eye varies at the DRAM. The green color eye uses 34 ohms ODT. The light blue uses 40 ohms. Orange eye uses 48 ohms. And red eye uses 60 ohm ODT. As can be seen, the center voltage varies with ODT settings. Note that not only at the 1 DRAM, but the center voltage also can vary at different DRAMs due to different loading effects. During the write cycle, the algorithm for the VRF training is specified in the JEDEC spec as shown here. During the read cycle, you will need to know how the VRF training is done by the particular vendor. I'll show you in the demo on how those options are set in the DDRX Wizard in HyperLynx. It is important that proper VREF needs to be considered so that you are making timing and SI measurements at the correct voltage level. So the way to reduce system power with DDR4 is to maximize the number of highs being driven. This is where the DBI feature comes in handy. If there are at least 5 DQ signals in an 8-bit lane which are driven low, then all bits are toggled and then DBI signal is asserted low to indicate that the inversion has taken place. DBI potentially will have more effect on simultaneous switching noise, which we will not be performing in this webinar. Before getting into some details of how margins are calculated on a data signal, I want to explain the device uncertainties. Uncertainties between the signal and its reference signal always exist in both the controller and at the DRAM. Here, the timing relationship at the controller between clock and ACC signals at the top and between DQS and DQ signal at the bottom. At the controller, there is 180 degrees phase shift between clock and ACC, but there is 90 degrees phase shift between DQS and DQ signals. The solid green areas define the uncertainties, which is the window in which the signal can occur with respect to the clock edge. Therefore, to calculate the worst case setup and hold margins, these uncertainties must be accounted for. At the DRAM, there is no phase shift between DQ and DQS, but we need to define the uncertainty for the data read operation. Now let's talk about timing parameters needed for the data bus for write and read cycles. For the write cycle, JEDEC specifies the requirements at the DRAM. HyperLynx provides the JEDEC compliant files, but the controller needs to specify the uncertainties between the DQ and DQS. For the read, JEDEC provides the uncertainties, but the IMAS requirements have to come from the controller vendor. Here is the data I generated by HyperLynx. This I is not simply created by wrapping all of the data bits, but must also include the DQS sampling positions as well. In other words, HyperLynx builds up the receiver I bit by bit based on the particular behavior of the DQS signal. Now we need to calculate the margins on the data I. Here are setup and hold margin measurements. Here are the noise margin measurements against the VRF and against the top and bottom of the eye mask. Pulse width needs to be verified also. For the address signals, again, we need the uncertainties at the controller, but the JEDEC provides the setup and hold requirements at the DRAM. HyperLynx provides the JEDEC timing requirements as we do with the data nets. For the ACC signals, you will want to understand how slew rate derating factor affects your margins. When any memory vendor defines the setup and hold times for their component, they use an input signal that has 1.0 volt per nanoseconds input slew rate. If you have a signal that has a slew rate faster or slower than 1.0 volt nanoseconds, it does not make sense to still try to satisfy those requirements. Therefore, you must derate or prorate on the signals specific to your design using the derating table provided by JEDEC as shown here for two sets of different data rates. I can point out that if the slew rate of your signal is 1 volt per nanoseconds and clock is 2 volt per nanoseconds, since it's differential, then the derating numbers are 0. But if the ACC signal slew rate is faster than 1 volt per nanoseconds, the derating factors are now positive. That derating factor will be added to the base requirements, hence decreasing the overall margin. But if the slew rate is slower than 1 volt per nanoseconds, then the derating factors are negative numbers, hence reducing the setup and hold requirements at the DRAM. Therefore, you might want to control the slew rate if your controller supports it to maximize your margins. Finally, to calculate the worst case setup margins for an address net at a pin, you will need to make the setup measurement between clock and the signal, subtract the derating factor and uncertainties at the controller to determine the final worst case margin. The same calculation needs to be made for hold margins as well. Another topic worth understanding in DDR4 design is why we need flyby topology and right leveling. As you can see from the screenshot on the left, from a real DDR4 design, the clock net is routed with flyby topology. Keep in mind that all ACC signals are also routed with this topology. This topology is better for signal integrity since the stub length to each DRAM pin is reduced significantly compared to previous multi-drop topology. But the DQS signals are routed with point-to-point topology as shown here. JEDEC requires that clock and DQS arrive at each DRAM pin within a certain tolerance, but the flyby topology introduces large skews between those signals at each DRAM. This has to be compensated by the controller by inserting the skew delay for each DQS as shown on the right by inserting the delays for each DQS shown by T1, T2, T3, and so on. Most of the DDR4 controllers should support this feature, but it's always good to verify. There is another functionality that some controllers offer is the data bit calibration. This feature tries to center the sampling DQS edge to the center of the eye by adding unique delays to each bit or one delay value per byte lane so that the setup and hold margins are balanced. In this example, you can see that the data mask signal setup margin is off balance without the bit calibration turned on, and the worst case margin with the uncertainty subtracted is failing by negative 14 picoseconds. You can also see from the margins for all other signals that there is less setup margin than hold margin. With the bit calibration turned on, the setup and hold margins are now more balanced. The takeaway here is that if the controller doesn't support this feature, then the length matching becomes very critical on the board for the eye mask to be centered within the eye on the time scale. Please note that JEDEC requires you to meet differential signals with these requirements as well. We'll not be going into details in this webinar on these measurements due to time constraints, but to be informed that it is impossible to verify all of these requirements without a simulation tool. Just to recap, I explained using this table that there are many JEDEC requirements, layout, and device electrical effects that you need to include to verify that you have plenty of margins. You will want to do this before fab out by simulating. If you have plenty of margins in simulation, which idealizes some of the effects such as the PDN and return path effects without the power aware simulation, then you can be confident that at least you will have enough margins in the lab. I explained briefly how pod combined with DBI saves power in DDR4. I explained why we need VRF training. I also explained our requirements for data nets are specified by JEDEC, but controller vendors should provide you with that data. I also explain how derating factors can affect your margins on ACC signals if you don't control the slew rate. I show how to derive the worst case timing margins for the ACC signals. I explain why we need right leveling due to flyby topology on the clock signals. Finally, I also mentioned that there are many JEDEC SI requirements that you need to meet for the differential signals, which are the strobe and the clock signals. Understanding all of these concepts might be overwhelming for some, but the DDRX Wizard in HyperLynx makes the verification process easy and efficient. It's good to have a basic understanding of how DDR4 bus works, but you don't need to understand the JEDEC spec in details to use the DDRX Wizard. It automates the process by running many advanced algorithms in the background, such as determining the derating factors, what the VRF should be as defined by JEDEC at each DRAM, creating the data I with IMAS placed automatically while accounting for the DQS edge position for each bit, and so on. All you need is IBIS models at the controller and at the DRAM. If you don't have the models yet, early in the design cycle, we provide a script and generic models which will fit your design pinup. You will need to provide timing info for both at the controller and the DRAM, but HyperLynx provides the JEDEC compliant DRAM timing files. For the controller, we provide a wizard to create the timing file. And you will need the design layout file in CCE or Hype or ODB++ formats. You set up the wizard and simulate to get the HTML reports, waveform files, and eye diagram plots. The DDRX flow we recommend is you derive the routing constraints by simulating in pre-layout stage to have plenty of margins early in the design cycle. You pass those constraints to a layout tool and route the board. But let's say you just follow all of the routing rules provided by the device vendors, you will still want to verify in the post-layout stage that your design have expected margins by considering all of the electrical factors I covered earlier. I'll demo these two steps in the design flow in this webinar that's highlighted in red. We will cover the other analysis in this flowchart in separate webinars. Now I'll demonstrate the design flow using this design in HyperLynx SI-PI, which has both memory down and two SO-DIMMs plugged into the slots on the motherboard. Let's look at the topology of some nets on the memory down interface. First, we'll look at the memory down topologies. We'll select the byte lane 0 and byte lane 7 and look at the routing. The lengths in each byte lane are well matched using the serpentines. Now let's take a look at the clock differential pair. You can see that it is routed with flyby topology. If we take a look at one of the address nets, you will also see that it is routed with flyby topology. With one of the DQ nets selected on the memory down interface, you can see currently there are no models assigned. You might be in the very early stage of your verification process that you might not have models from your vendors yet. In this case, we provide a script that you can run to assign generic models to your interface to give you an idea of how your routing is performing electrically. Simply select an address signal to provide the ref des of all the devices in the DDR4 interface to the script. You also have an option to assign generic model to a particular ref desk. We'll use option 1 in this case. Now let's check that generic models are assigned at both the controller and the DRAMs. Now with DQ63 selected, turn on crosstalk. Aggressors are brought in according to the threshold currently set. You have an option to take a look at where the coupling is strongest and weakest by walking through the coupling regions visually here. Next, let's run interactive crosstalk sweep simulation on DQ63, which is currently stuck high with other two aggressive switching. We will sweep 3 different drive strengths at the controller. When the simulation is complete, look at the victim net's DRAM crosstalk value with stronger drive strength. You can see it's about 21 millivolt, and the weaker drive strength, you can see it's around 14 millivolt. Now let's simulate using DDRX Wizard with the generic models. I've loaded the DDR file with every page already set up. You need to define the interface as DDR4, and we are running at 2666 megatransfer per second in this case. You can see that generic models are assigned. We'll just simulate data and address nets. You can enable a DVI setting here. The signals on each DRAM are grouped automatically here. We're just going to enable only a few address nets and byte lane 0 and 7. Assign the drive strength and ODT values for the data nets here. For the ACC and clock signals, you can set the drive strength from here. We will assume that this controller has bit calibration for both read and write cycles. From the timing model page, you can see the ideal timing models is assigned, which has 0 uncertainties and 0 requirements for the eye mask. For the DRAM, as mentioned previously, JEDEC compliant files are provided as part of the HyperLynx installation. Here is where you will set up the VRF training for the controller. You define the stimulus here and enable the crosstalk option if you want to see its effect on timing and SI margins. We will simulate 2 worst corner cases. The JEDEC quality check limits are predefined here for you. You can also enter the meaningful name to the result folder here and run the simulation. We can take a look at the results I've already run using the report manager. Let's compare the results with drive strength of 34 ohms and ODT of 40 ohms on the left, and the drive strength of 48 and ODT value of 48 on the right. You can see that the margins are slightly better on the left. You can also get absolute crosstalk values on each victim net using the generic batch wizard. If we compare the results with stronger drive strength of 34 ohms on the left and weaker drive strength of 48 ohms on the right, the stronger drive strength case is failing. the 30 millivolt crosstalk limit. So as you can see, the generic models are useful for trying to determine preliminary margins on your design fast and easy. Next, we'll simulate using the actual Xilinx IBIS models and timing parameters. From the ODT models page, you can see that Xilinx offers not only different drive strength, but also slow, medium, and fast slew rate driver options for the data nets. It also offers the same choices for the address and clock nets. I'm using the timing parameter values provided by Xilinx in this case. Here are the timing relationships for address and clock. And here's the relationship between DQ and DQS. The read I mask parameter are also provided. To create this file, we provide the timing model wizard as shown here. You can go through the pages and enter the values as provided by your vendor to create the timing file. Now let's take a look at the simulations I've already run. The first report contains results for byte lane 7 for both read and write with slow edge rate of drive strength 48 with 40 ohms ODT. You can see the results are failing for write, indicating that slew rate is not fast enough. The read case is passing with pretty good margins. Now let's just concentrate on the write case of byte lane 7 with fast edge of drive strength of 48. You can see that monotonicity check is failing. Now let's take a look at the medium slew rate of drive strength 48. You can see now that the timing and SI checks are now passing. Let's take a look at the eye plots for slow corner case. The eye looks pretty good. Take a look at the fast corner case. The eyes look pretty good as well. Next, let's look at the crosstalk on byte lane 7 using the medium slew rate driver. I'm using the strong corner case only to see the worst case crosstalk. You can see that the crosstalk values are below 30 millivolt. You might be able to get better timing margins with stronger drive strength driver, but the crosstalk voltage will increase. Therefore, it's important that you make these trade-offs to come up with optimized drive strength and ODT values to maximize your margins. You can export just one DQS and one DQNet, for example, to LineSim and perform sweeps there as well. We will cover those pre-layout simulations in the next webinar in the series. Finally, let's look at the report containing the address signals with slow slew rate out 48 driver. There are many timing and SI failures. This indicates that you will need a faster slew rate driver. Let's open up the report with fast slew rate out 48 driver. You can now see that the design have plenty of margins. In this demo, we only looked at one byte lane and a few address nets for sake of time. But it is recommended that for design sign-off, you verify the entire bus in one run for all corner cases for data read and write, the ACC signals, and skew requirements between DQS and clock. You should enable trace-to-trace and package coupling effects and the DBI option to report the most accurate margins. The simulation time will vary depending on how many bits you use as the stimulus and the crosstalk threshold set. Here I have one data net selected on the SODIMM interface, which propagates from the controller through two connectors and to the DRAMs. If you enable crosstalk, it brings in two aggressor nets shown by dotted lines. Now let's enable package coupling by DB. And now it brings in additional aggressor net. Let's take a look at the VIA on the motherboard. You can see it's a blind VIA. If we take a look at the VIA, one of the VIAs on the DIMM, we can see that it's a through-hole VIA. If you look at the number of loads on the data net, there are two loads, one on each DIMM. Now let's select an address net and observe the number of loads. There are 4 loads on the first DIMM. Since the DRAMs used are by 16 device, so you will need 4 DRAMs for 64 bits. You also have another 4 loads on the second DIMM. So the ACC nets will have 8 loads total in this DIMM configuration. Let's take a look at the setup in DDRX Wizard. It's set up as 2 slots, 1 rank system. For multi-rank systems, you now have dynamic termination option, which allows 3 ODT states. You can see the settings for those 3 states from the ODT models page. On the ODT behavior page, you have the option to set the ODT at just 1 DRAM, or you also have an option to enable another ODT value on the other DRAM, for example, a weaker ODT value. In this example, I have a stronger ODT of 48 ohms on one DRAM and weaker ODT of 240 ohms on another DRAM. Now let's take a look at the simulation results I've already run. In the first report, I am using the 40 ohms medium slew rate driver on byte lane 0 for the write operation with ODT value of 40 ohms at the DRAM being written to. Both the timing and the SI results are failing quite badly. Let's look at the read cycle results, and they look pretty good. Let's look at another report with 40 ohms fast slew rate driver with ODT value of 40 ohms on the DRAM being written to. The results look slightly better, but the margins are still failing. Now let's look at the report with 40 ohms fast slew rate driver with ODT value of 40 ohms on the DRAM being written to, but also a weaker ODT of 120 ohms on the other DIMM DRAM. Now the design is passing with some margins. Next, let's look at the results on one of the address signals. Comparing the results with different drive strength of 40 ohms medium slew rate driver on the left versus 40 ohms slew rate driver on the right, the fast slew rate driver produces higher margins for both fast and slow corner cases. We will now look at an address net with 2 ranked DIMMs in the system. If you look at the number of loads on one of the DIMMs, you can see there are 16 loads since the DRAMs are by 8 devices, so you need 8 DRAMs to form one rank of 64 bits. Since this DIMM has 2 ranks, you have additional 8 loads. If we look at the second DIMM, there are 16 more additional loads, so the ACC bus will have 32 loads on each NAND with this DIMM configuration. If we look at this setup in the DDRX Wizard, on the DRAMs page, it is set up as 2-slot system with 2-rank DIMMs. Now let's look at the simulation results on an address net driving with the strongest and fastest driver available for this 32 loads configuration. The first report shows the results running at 2666 megatransfer per second, which are failing badly. Next report shows the results running at 2400 megatransfer per second. Some setup margins are passing, but hold margins are mostly failing. The third report shows the results running at 1866 megatransfer per second. The results look better, but you can still see some failures on some DRAM pins on this address net. The final report shows the results running at 1600 megatransfer per second. Now the design is passing with good margins. In summary, different possible DIMM configurations can bring more analysis and design challenges. In this case, you need to inquire with the controller vendor if it supports higher drive strengths, or you need to inform the users that your board will support only a certain maximum data rate for a particular DIMM configuration. At this point, I would like to point out that we have these 2 post-layout workshops available for you to download to try out the functionalities I've demonstrated in this webinar. The workshops contain step-by-step instructions, models, and design database, and needed scripts to perform the tasks in HyperLynx as IPI at your own pace. If you're interested, please click on the Contact Us link below and provide us with your contact information. I would like to thank Syntax for letting us use their design for today's demo. I also like to thank Micron for the DIMM files and the DRAM models. And thanks go out to Xilinx as well for their FPGA IBIS models. So in summary, I provided some insight into why just following the routing rules is not good enough in DDR4 designs running at high data rates. I listed and explained some of the electrical considerations you need to make during the post-layout verification process to verify that you have plenty of timing and signal quality margins. I demonstrated how to optimize design margins in the post-layout simulation using the DDRX Wizard in HyperLynx SIPI. And finally, 2 DDR4 workshops are available for download. One uses the vendor-specific models, and the other one uses the generic models. Thank you for attending today's webinar. I hope this information was useful for you. Now I would like to open up for a Q&A session.